Hi everyone. Today we're going to talk about Siphon. This is basically PostgreSQL to everything without breaking production. Before we proceed, just a small disclaimer. This information provided is presented in this presentation represents personal opinion of presenter, and just to ensure that GitLab, it do not says anything about GitLab. It's just a personal opinion. And about me. So I'm Ved Prakash. I work as a staff data engineer at GitLab. I've been at GitLab for 4.5 years, and before that I've been working for 11 years with a company called Infosys Limited, and I've been doing just data for last whole 15, 16 years of my life, and this is me. And something about GitLab. At GitLab, our mission is everyone can contribute. GitLab missions of everyone can contribute reflects our belief that innovation thrives when barriers to participation are removed and every voice has the opportunity to shape the future. At GitLab, we live with our credit values, and these are the 6 credit values which we live every day. We believe in collaboration. Our results are focused for our customers. Efficiency is something which we pursue every day. Diversity is where every one of us at GitLab across we are like 2,400 employees, and we are across the globe. As it is a 100% remote company, we believe over there. Iteration is that we believe in fast iteration to improve it continuously. Start small and keep iterating better. And transparency, we default to transparency by documenting decisions, sharing information openly, and making our works visible, creating trust, and enabling everyone to contribute. So what GitLab is doing? What is GitLab? So GitLab is the DevSecOps platform delivered as a single application, unifies historically separate development, security, and operational tools into one coherent ecosystem, eliminating integration headaches and communication silos that typically slows down the team. And this, the central data platform team, part of the data platform team, which I belong to, is part of the central data team. And the data organization at GitLab works in a hub-spoke model, and over here the data platform team serves along with analytics engineers and other data analysts and data science teams to the different business domains within GitLab. Siphon, this is in beta. It is under active development at this point of time. And with this, just like to dive in further, the pain point, what we faced at GitLab and what production challenges we face. We would like to highlight that, a brief on that. So production database under pressure, that's one big thing that you'll see in the all upcoming slides, but there were certain sections, like there was a performance crisis in terms of analytics queries competing with transaction queries. We wanted to run certain analytics on top of our monolithic database. That was one of the performance things. The data refresh used to take like 10 to 12 hours of freshness lags, and database polling overhead. So extract data out of Postgres, there's lots of streaming, but we were doing polling because of, in the upcoming slides, we'll show that it is a monolithic architecture over there. Operational nightmares, as a data engineer, it's like backfill takes forever. If we introduce to backfill a table which is of like 400 GB or a terabyte, it's just running for like a couple of days in the backend. A schema change is equal to broken pipeline, manual recovery interventions, high infrastructure cost on this. This leads to the data quality issue because there was multiple extraction mechanism to extract the same data. Data was going to different data stores like Clickhouse, Snowflake, Iceberg, but the mechanism to extract data was different, and which lead to a different time or different state of data was getting extracted, and which lead to the nightmare for the analyst engineers to correlate all those data stores and see that it is all matching or not. And not end-to-end any data governance over there. And the monolithic infrastructure, so the biggest challenge what we had was it can't enable logical replication on primary instances because that's where the GitLab as an application is running. And we don't want to overwhelm it with the amount of CDC what GitLab generates, which is approximately close to it is a 1 year before matrix, it was 100 GB CDC per hour happening on the system. That much amount of data, logical replication had some limitation at that point of time. Heavy traffic would overwhelm the systems. Risk to destabilize the production. And modern data stack requirements, which was evolving like ClickHouse, where we run lots of our analytics metrics about that. We need a sub-second analytics query, CI/CD analytics dashboards, real-time usage metrics, all runs on ClickHouse. Then we have a Snowflake, where all the business intelligence, complex transformation, and historical reporting happens, where we are tying this data with all other data sources which we get at. Lots of need and lots of requirements were popping up for real-time data streaming tools, basically towards the threat detection and the threat detection kind of requirement at GitLab. And these data needs to be streamed. And the lakehouse. Apache, we can't end the story without a lakehouse thing. Long-term storage, data lake architecture, and cost-effective archival. These were the requirements what was coming up. With this, I would like to just recap on why we built Siphon. It was operational nightmares, data quality issues, performance, different team, different technologies, and monolithic at the end. The solution what we came up was Siphon, a real-time data replication engine. So what is Siphon? Siphon is a tool used to replicate data from PostgreSQL database to other data stores by reading the PostgreSQL logical replication stream. It's nothing new. Lots of tools are in the market which does the same thing on this. Just the way we have written, we feel it works good for in-house. We went with the whole process of evaluating build versus buy with all the process. And we moved towards that we will build it in-house because our data source is always fixed. It's PostgreSQL. It's not changing. That's what one data source, but different data stores, that's the destination. Data emitted or changed or inserted once should get captured to 3 different data stores for different analytical or different requirement purpose. So Siphon works with, it's written completely in Go. That's where it is right now in the schema tracking is under development at this point of time. Multi-destination is built. We are writing data right now to ClickHouse, Snowflake, and Iceberg. And monitoring is also in build, which we'll discuss a little later in the slides. We are using this, coming back to the solution architecture, and just what's calling. We have the PostgreSQL source database, which is basically from where we capture all the real-time changes. We have that replication manager, which is Siphon producer, which is debugging, reading all this PGP output messages, capturing the CDC out of that, and pushing that to NATS Jetstream. So we are using NATS. It's one of the lightweight queuing system which we have been using, and it's quite effectively working good with the performance. And another one is for a snapshot manager. That is for initial data, what we want to capture full table copy. And from there, the data, from NATS, the data gets to the Siphon consumer, and it can be a different consumer which is built by the each of the team, different team. So for analytics, it goes to the ClickHouse, warehousing to Snowflake, and data lake to Iceberg. There are 3 different consumers. Right now, actively working is data lake and Iceberg consumer and ClickHouse consumer in this point. And this is the overall high-level architecture looks like. So what was the feature which was, so Siphon is like non-invasive design. This is built like use Postgres native features only. We don't install any additional plugin on it because that was one of the biggest no from our database reliability engineers that we should not install anything on top of production instances. So it uses PGP output, PG output plugin, logical replication slots, both comes by default in Postgres. No tracking tables is created on this database system, so that makes the life of DBRE very much relaxed because they don't have to maintain something which is not there. No triggers is there, which triggers the data that one insert has happened, it writes to somewhere else. And the best at the end is that your database stays exactly as it was designed. So no changes which happen. So with this, what was the biggest benefit is that you can plug it out if something just breaks. For example, Siphon is creating an overload onto the system. Just drop the replication stop and your system is just stable and as it is. There is no impact. Risk-free testing. So if you want to test Siphon, can't break production database because we read from the read replica, but it is just emitting the message out passively, not waiting for someone to consume it. So built by asynchronous by design. So that's where it's the asynchronously helps us to do. No data written to source, so that's a compliance friendly as well, and version upgrades. So we don't have to worry about the plugin upgrade. As Postgres upgrades itself, the plugin gets upgraded by itself. So why this idea was like a brilliant for us? Zero impact on production. So it reads from read-only replica, require minimal locking on the primary. The locking only happens when we create a new table, and that's the minimal locking. It tries to lock the system to take a snapshot point from where it has to send the full backup of the data, while the time the logical replication keeps capturing the real-time streaming happening over there. No additional analytical queries on primary. Primary is just for transactional, no one touching that, and asynchronous by design. So it is the PG output is just responsible to emit the message. The producer is responsible to consume it, but if not consuming, it do not impact the application. The data consistency gets guaranteed with this. So we try to preserve the transaction boundaries of the data. Once the data gets emitted out of Postgres and it's consumed by once the producer consumes it and decode and push it to the NAT just stream, that's where the boundary breaks. And from there, it's the responsibility of the consumer to write the data to the sources. At least once delivery semantics. So in case of failure or in case of restart, we try to do it, the Siphon as a tool, try to at least do delivery once. In case of restart, there is a possibility to making duplicates, but that's how we have built the consumer, that it is responsible to ensure the uniqueness of the record. Automatic recovery of the failures is part of this. Sub-second latency. This was one of the requirements for the threat detection team, that they wanted the data on the real time. On the streams, they can just hook to the real stream and see if someone is trying to play around with the application. No polling overhead. We have right now the mechanism a certain team is doing that are running a database query based on an incremental timestamp to pull the data out. That creates an overhead on the system. Even though you read from a read replica, we are reading from a snapshot. It creates a lag and direct stream processing. So the data is getting streamed as we process. Smart wall decoding. We are doing a parallel wall decoding, a schema caching to avoid lookups, and memory efficient buffering. So while the time memory efficient buffering comes a lot when we do a backup, when you try to instigate the logical replication for a new table, and that table is huge, by the time the snapshots gets moved to the target data stores, we buffer all the CDC happening for the time being into memory, and once the backup is persisted into the target data stores, we push all those changes to the target data stores. Multi-destination router, rule-based routing, per destination batching, and automatic retry with backoff. Rule-based routing is basically that one data events or one particular table is required by, you saw in the architecture, there were like ClickHouse, Iceberg, or Snowflake. Snowflake needs to consume 10 tables, whereas ClickHouse needs to consume 2 tables. And 2 tables are the common. So one event has to be consumed by 3 consumers, and one event just has to be consumed by 1. So that rule-based routing has been defined. It's defined in the config that this particular table the event has to be consumed 3 times before it gets dropped from NAT just stream. As we scale, we move towards the adaptive batching. So we batch our data sets to persist into the data stores to ClickHouse, where ClickHouse works very good with the merge tree concept, where you just batch the data and put it right to ClickHouse, and the ClickHouse itself take care of updating, keeping the record unique. So multiple direct inserts was not a good, so we moved towards adaptive batching. The same works for Iceberg and the same works for Snowflake as well. Ring buffer for wall messages, that's for the memory management, off storage for large object, and automatic memory pressure detection. So if we are breaching or putting a lot of pressure on the NATs to keep the real-time logical replication buffered, we have that mechanism of detecting it, and based on that, we try to take action that where do we persist. Still in beta, so we are still learning a lot of some break here and there, but that's the plan. Connection pooling, per destination connection pools, health check, best routing, and automatic failover. That's built as well. And for monitoring and observability, we have the complete visibility, YAML-based configuration for this. We export our metrics to Prometheus, and the metrics which we capture at this point is replication lag, second message per seconds, error per destination, and memory usage by bytes. These are very high-level things. There are much more which is present in our repo, which is open to see and open to contribute. It's getting production ready. So that's the, with these features, we want to have a checkpoint management, persistence, LSN tracking, automatic resume from last position, and no data lost on restart. We are working as still, we have tested the no data loss a lot. That works good. Automatic resume from last position is very well tested as well. We are saying production ready, but it's not in production because since it is beta, but in coming 1 or 2 months, it will be moving to production as well. What we learned that logical replication is ready from, Postgres logical replication is production ready from read replica. So from Postgres 16, logical replication is possible to read from secondary instance rather than the primary. So that's one of the biggest benefit what we had, and that's what we took, that it is possible, easy deployments, handle billions of changes daily, which is what the GitLab volume is at this point of time, and minimal overhead on the primary instances. Excellent concurrency. So we used Go to write this whole producer and consumer, but not all the consumer apart from Iceberg. Iceberg consumer is written starting with Go, but it ends in PySpark to persist data to Iceberg. And we use open catalog over there from Snowflake provided. Low memory footprint and easy to deploy. It's just single binary. We just able to deploy it with Helm chart that we have released. And simplicity wins. That's another one tool, multiple destination, one source, same data has to go multiple. This is the unified monitoring and single configuration. And with Siphon is an open source, so this is a QR code. If you scan, or you can go to the Siphon repository, and over there you can see all the documentation and the codes around this. It's built with MIT license, so it's present for use for the contribution. Anyone interested in writing Go code and want to write a consumer for a particular destination, please open an MR over there, and we are happy to look into it. And with this, I'm coming to the end. So what we learned is that don't fight the database, just embrace it. Postgres SQL logical replication is a superpower waiting to be unleashed, because we believe this was something which is present in DBZM and lots of other tools like PeerDB, RT, all are using logical replication. We wanted to just not install additional plugin. That was one big thing on the production. And reading from read replica, that was a game changer for us. And this is me. Anything about me, if you want to ask any question around this, or in general about how we have built it, or any data practice, please connect me on LinkedIn. This is my LinkedIn QR code. And with this, would like to open the forum for question. Anyone?
Okay. Thank you. So, do we have any question in the room? No, I haven't seen online questions. So maybe one question I had. Do you think this tool can adapt to other source, or is it really linked to the PostgreSQL logical replication?
Sorry, come again?
Do you think it can adapt to other data source than PostgreSQL?
It can adapt to different source, but at this point of time, we have just made it from Postgres to different sources. That's the USP, that we are not making a different producer. We have one producer, but we can extend your consumers. So if we are writing right now to 3, and there is a 4th one is real time. So this is what we are saying, that an event produced once can be consumed by n number of consumers for a different analytical purpose. So,
okay. And in your design, you plan for possibly adding more consumer to export to different other systems.
Sorry?
In the design, you had...
Like to have more consumer, yes. But at this point of time, since it is beta, the target is that we make it stable for these 3 consumers plus the real-time analytics. And once it is there, then yes, we depends upon the use. Right now at GitLab, the use case was 3 data stores, which we are using extensively.
Okay.
Once it becomes like we need another one, there are lots of other internal use cases where the Siphon fits in to move data logically from one Postgres instance to another. So it might be a Postgres consumer only written at the last. But yes, there is something in pipeline.
Okay. No question in the audience? Okay. And maybe one question, just a naive question. Maybe I think every developer uses GitLab somehow and at some point in his career. Yep. From a user perspective, what is the kind of data that I have in GitLab that you transfer with this tool?
To our system. So from the GitLab, what data we bring it to our analytical is just like engineering metrics kind of thing, like how many issues are created. Okay. We don't bring any red data, like any customer data, we don't bring it in. Okay. It's all filtered out, and we only bring our internal projects data sets inside, and it's more about to know how the product is being used. Is it like where it is, which feature is being used, which feature is not being used, where it is getting overutilized, what is getting underutilized. It's just, there is two aspects. One is product aspect, and there is an engineering aspect to measure the engineering efficiency, and that's where. So we don't bring customer data to a Snowflake. That's something it's written in the handbook. So yes, it's publicly written, and that's what we do.
Okay, that's very clear. Thank you very much again, Ved.
Thank you. Thanks a lot.